Okay, so this week we are focusing on constraint optimization. So finally, we can start to handle constraints. And actually, they are quite troublesome. Because in the unconstrained optimization, we don't need to worry about some other functions. We just worry about the objective function. And the entire design space is there for us to explore. The algorithm will choose its own way to find the proper solution. So just follow the solution procedure, follow the equation that was derived, and keep solving it until it converges. If the function is properly convex and solution exists, the algorithm should be able to find the solution, unless it's not a convex function, like a concave. What is a concave function? If you have like a sine function, you can say it's concave because too many ups and downs. Okay, so back to the constraint optimization. So let's write down a general formulation. This time, I think I'll do this. Okay, so this is the general form, and every function in here can be nonlinear. How do we transform this equation into a standard form for linear programming? So when we use this method, linear programming, obviously you are dealing with some linear functions. So when we face this general optimization formulation, we have to do something to make everything linearized. Okay, so how do we linearize? So they are all functions can be nonlinear. But for linear programming, we need to linearize. Linearize all functions. Okay, so for LP, we can only handle optimization problems which only has linear functions. So here is a f of x with a bar on top. So it's a linear approximation of the original function. So you can say something like this: f of x is similar to f bar, and f bar is gonna be the first order Taylor expansion. So how do you write down first order Taylor expansion? Here you can use any expansion point. So x0 is my expansion point. Okay, and then dot product right here, gradient. This is basically first order Taylor expansion. So this is how you can linearize a function. And from here you can tell if you do this, you are not solving the original problem. You are solving a simpler problem which has been simplified by the linearization process. So it's an approximation. The solution you get may not be the solution for the original problem. So in the future, later on, I can tell you what people usually do when this is happening. But at this point, we don't care. Next. So do the same for g, function g and h, if they are nonlinear. Okay? Basically same function. So now let's say we already have everything linearized, but for LP we don't like one thing. We don't like inequality functions. So we need to convert inequality functions into equality ones. So inequality constraints needs to be converted to equality ones. Okay? So how do we do that? Let me show you 2 examples. Okay. Here's one example. 3x1 plus 2x2, which is has to be smaller than 3. Okay. And another example is 3x1 plus 2x2 must be larger than 3. Just 2 examples. So how do we convert them? Okay, we will copy everything on the left hand side, and then we will introduce a new variable, and here minus t. Okay, for the right hand side, convert everything into equal sign, keeping the right hand side. Okay, and also s must be positive, t must be positive. So what is s and t? S is so-called the slack variable, and t is called the surplus variable. Why is surplus variable using t? Because s being used. That's why I use a different symbol. It doesn't matter, just a symbol. Okay, so what's a slack variable? What's a surplus variable? When I first learned about this, I have no idea about the meaning slack. So I translated to Chinese. I still don't understand why it's called slack. It's actually about relaxation and of the function. So don't worry too much about the name. Just please learn how to use it. So one important thing for this approach, the right hand side right here, has to be larger than or equals to 0. Okay? This is the format. So how about another example? If I have this smaller than negative, what do? You can multiply -1 for for the entire equation, then you will have this. A multiply -1, so the sign changes. It becomes larger than or equals to. Now you can introduce the surplus variable. Okay. Now let's take a look why this is okay, and why are we setting up certain rules. Okay, so LP is being derived in a certain way. The general optimization formulation has to be transformed into certain format. So this is for the preparation of that standard format. And for linear programming, later on for the constraints, we will have constraints, right? For the constraints, and we are going to convert all the inequality constraints into equality ones, and on the right hand side of the equal signs, linear programming wants the coefficient on the right hand side to be positive or 0. That's why it's setting up certain rules or certain ways to get those equations with coefficients on the right hand side, which is positive or 0. Now, if you look at this equation, okay, and look at this one. Now take a look at the slack variable. The slack variable has to be positive or 0. So that's in the case of 0, then this equation equals to 3, right? And if s is positive, this equation right here will be smaller than 3. So for both cases, equal or larger than, this left term is going to be either equals to 3 or smaller than 3, which is equivalent to what we had earlier. So in optimization, we do this kind of things a lot, actually. We face a kind of equation that may not fit the format that I like. I can actually modify a little bit, but ensuring the new equations is equivalent, new equations are equivalent to the original one. Then you can replace it, because doing this is the same as doing that. In optimization, this is okay. Can you say they are the same? No, they are not the same anymore. You introduce something new, but the solution will be the same. In optimization, these two sets of equations are basically equivalent. Okay? So in the future, when you describe what you are doing, I recommend you to describe it precisely. By introducing the slack variable, you generate equations that are equivalent to the original one. But you cannot say, by introducing the slack variable, I got the same equation. They are not the same. They are slightly different, but they are equivalent for solving optimization. Okay? Now, let's take a look at the second example. This time, because we have this larger or equal sign between the left hand side and the right hand side, we will introduce the additional variable with a minus sign in front. So we call it a surplus variable. But doesn't matter. I mean, for me, it's like basically new variables. and the difference between them is one is positive, one is plus, the other one is minus. Okay, and both select variables and surpass variables, they are positive. Okay, so consider the equal sign, t equals to 0 case. This term equals to 3. Okay, consider the positive case. This term minus something positive equals to 3. Then 3x1 plus 2x2 must be larger than 3. Right? So that's how you can observe and realize truly the new equations are equivalent to the original equations. Okay? And here's the last example shows you what you should do when you have negative values on the right hand side. You should multiply -1 for everything to convert the right hand side to positive. Then you can do the trick that we I made a mistake. Here is minus. Sorry. This is minus. Right? Because here is larger than or equals to. So I should minus surplus variable. Okay? Now if you can do this, we have the original f being linearized into a linearized f. We have g functions which are inequalities, and we use the trick of introducing new variables to make them equality equations. And originally we have equality equations. So after all these, we will have linear objective functions and linear constraint functions. Every one of them are equality constraints. Okay? So after all that, we will have a form like this. There's a reason why I'm writing this in this way. Let's say we have n variables. Okay? So supposedly I will have Cn, Xn, A1, n, Xn. Okay? And here's B1, Bn. Oh, Bm, actually. Okay? We should be able to write everything down in this way. And also, very important, for linear programming, we can only handle everything positive or equals to 0. So this part is very important. Okay, and also all the b's are positive or 0 as well. If you end up with a format that doesn't follow the sign right here, then LP doesn't solve it. So you must do something else to convert your equation into this form. So someone may ask, how about a problem like this? Just a very simple one. Okay. We in this case, we are dealing an issue. You allow x1 to be negative, then this doesn't fit what linear programming wants. So at this point, you can do something. You can do some shifting. You can introduce, let's say y1 equals to x1 plus 2. So you end up with minimizing y1 minus 2 plus 3x2 subject to you will have no, I did it wrong. Plus did I? x1 y1 minus 2. Yeah, correct. So you will have negative 2 smaller than 1 minus 2 smaller than 5. So which is actually plus 2 on everything. So 0, y1, 7. And same thing for the x2, right? So you end up with linear objective function inequalities, but everything is either positive or 0. And you can do the rest because the constraints right now, they are inequalities. You need to convert them into equalities. Let me show you. So what do you do next? You actually have 4 constraints. You will have y1 larger than 0, y1 smaller than 7, x2 larger than 0, x2 smaller than 6. They are actually 4 inequality constraints. Now introduce select variables. So I'm gonna, for the smaller one, I introduce select variable. So this is, I'm gonna call this S2, okay, equals to 7, and this one x2, I'm gonna call this one S4, equals to 6. Okay, and over here they will be surplus. So y1 but minus s1 equals to 0. X2 minus s3 equals to 0. They are actually becoming equations like these. So how do I write them down in the standard form? Let me show you. I already introduced so many new variables. So minimize, okay, I should have y1 here plus 3x2, and actually I have new variables. So 0 times s1, 0 times s2, 0 times s3, 0 times s4. They are actually my the variables in the new problem. Okay, and then the coefficient minus 2, but the coefficient minus 2 doesn't matter because you know the constant values in objective function means nothing. You are not going to change them, and you are trying to find the optimal x, y, z optimal variables that minimize your function value. If the constant is 4, it's 4 all the time. If you eliminate the constant, just get rid of it, the solution doesn't change. So in fact, in objective function, we don't care about the constant value. However, some people sometimes make a mistake. Okay, I found the solution. Let's check on the function value and plug into the one without the constant. Your original problem actually has a constant. So you need to, when you try to evaluate what you have, don't forget about the constant. Okay, that's it. Now, how about what do the constraint looks like? I will have y1 here minus s1. I write it down here. y1 here, and then I will say plus s2 here. Okay, and I have x2 here minus s3, and then x2 here plus s4, and my equal signs and the constant values. And now y1, x2, s1 to s4, they are actually all positive, right? Since they, so I probably don't need to formulate these two because they are a part of the rules. So I am making this too complicated. So this is okay. If I do this, this is okay. This is definitely solvable. But when I do this, I introduce too many additional variables. So in fact, you can eliminate these two functions. That doesn't matter. So if you do that, you can eliminate these two functions. Because y1 positive, x2 positive is already given at the bottom. Okay, but by this example, I'm just showing you, you can convert inequality problems into equality problems. You just need to introduce some slack variables or surplus variables. Now, when I write down this format, why do I align all the variables properly? Why don't I just put them together? Because later on, we're going to convert this form into the matrix and vector form. So when we align them properly, it helps us. Okay, so from here, we already have the standard form. Copy. And then back to here, I'll just paste it here. So can we shrink it? Okay. So we can actually now rewrite this into a vector and matrix form. So minimize vector C transpose vector X subject to A matrix multiplying a vector X equals to a B vector and all the X positive. We can actually rewrite everything into this way. Why do we need the C vector to be transposed? Because the C is a vertical vector, and when you do a dot product, you have to transpose it. So what are those? Where I write down for you. C equals to basically C1 to Cn. Okay. X basically x1 to xn. A matrix basically A11 da 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 da, a lot of dots to A m n. Okay. Da 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 da. So the size is m by n. B vector is b1 to bm, and n equals to the number of variables. M equals to the number of constraints. After basically after you convert everything into this standard linearized form. Okay, so far it should be quite simple. Okay, the only thing is you have never solved a problem like this. Now, okay, there are some rules about number of the equations and number of variables. So we have three situations: n smaller than m, n equals to m, and n larger than m. So let's think about the easiest case, n equals to m, which means you don't need optimization, because if you have this equation right here, ax equals to b, and n equals to m, in this case your A is a square matrix. You can directly solve it by x equals to A inverse B. So you have one solution. If the A inverse is a proper matrix, then you can solve it. So there's no reason for optimization. There's one solution there, only one solution. So we don't deal with, for optimization, we don't deal with n equals to m, because there's only one solution. No need optimization. Okay? How about the case of more variables than constraints? Here, more variables. So in this case, let me see. Actually, I should talk about this one. More constraints. Yeah, more constraints than variables. More constraints. So too many equations. Because let's say n equals to 5, m equals to 6. For every 5 equation, I can already solve for one solution. But that solution may not fit the last equation, the 6th one. Then you may not be able to find solution. Too many rules. Okay, so solution may not exist. You may not be able to find a solution that satisfies all 6 equations. So this is the case what we can do. This is for LP. When we have more variables than constraints, so it's like a number of equations is not exactly the same as number of variables. Not too many is not enough. So when fewer equations, when we have fewer equations than number of variables, then we have a lot of solutions. There's so many possible solutions, but maybe only one is the optimal. Among all these possible solutions, we are trying to find one that's going to minimize the objective function. Okay? So we may have many feasible solutions, right? And we want LP to find the optimal one. That's why we we use optimization. Okay? Now we are clear about the standard format, and we are going to talk about how to handle LP problems. And the method I'm introducing right here is not the only way. Okay, if you Google for linear programming, there are usually 2 different ways. This is one of it. I forget the name. So anyway, this is the one I'm introducing. Now let's take a look at our problem, and let's try to write it down in a certain way. So it looks like this. Okay, let's do this. Okay, what is this? You will know later on. So your A may be A should be same length here. Okay. Yeah. I'm trying to draw the vectors and matrices, the size of them, in to represent the general problem. So basically, this is C transpose. This is your X, right? And this is your A matrix. And this is your X, and this is your B. Right? Okay? Now, when we try to solve this problem, we are going to handle the A matrix. And we are going to separate the A matrix into 2 parts. So the way we are doing it, before we do that, I need to remind you their sizes. So this is 1 by n. This is n by 1. Okay, n by 1. This is m by 1. So this is n by m. So here is n, here is m, right? No, reversed. Yeah. Yeah, reversed. Wrong. M by n. This is m. This is n. Yep. Did I make mistakes up there? No. Okay, good. Now, what we are going to do is to find a square area right here. Just separate them. Okay. So here is let me see. Okay. Square right here. So here is m, and here is n. No, here is n minus m. Okay. And we're going to call this part of the matrix A and capitalize B. Here is A and capitalize N. So what does the capitalize B and N mean? So B means basic variables. N means non-basic variables. Okay? So when we do that, we actually apply the same concept to everything. We will do this separation So here is gonna be CB transpose. Here will be CN transpose. We even do the same for the X. So right here is gonna be XB and XN. Do the same. XB, XN. Okay? But we don't do anything to the small b. Just like put a wall between numbers and call this group big B, call this group big N. That's all. Nothing fancy. But when we do that, they can actually be written as CB transpose XB plus CN transpose XN. Think about it. Is it correct? Alright, we can do that. So for the constraint at the bottom, actually it's gonna be A B XB plus AN XN equals to small b. We can do that. Okay, that's interesting. Now we are going to take a look at something on the XB. Okay, so from here, we can derive what is XB. So in fact, it's gonna be AB inverse times small b minus AN XN. Right? We move the second term to the right hand side and then multiply AB inverse. That's what you get in the end. Right? So that's something we are going to use later on. Actually, right now. We are going to plug in this equation back to our objective function. So our objective function now, we already have this part. Copy. And then paste it here. Right? And we are going to paste it again. And get rid of something here. We're going to plug in XB into this equation. So I just move this guy here, copy this guy here, paste it here, and then move like this. Just plug in. So basically, plug in. Okay. Now we can expand all the terms. So CB transpose AB inverse small b minus CB transpose AB inverse AN XN plus CN transpose XN. Okay. Now we can start to collect terms. How do we collect? We realize in this equation, in your objective function, there are a bunch of constant values. C is a vector of constant values. Small b is also a vector of constant values. Capitalized A is a matrix of constant values. So only thing that could be changing is actually xn. So let's just collect them. Put them together. So CB, the same thing. CB transpose AB inverse small b Now let's do this. Cn transpose minus Cb transpose AB inverse An and Xn outside. Vector. Yep. Okay. So what is this? This is basically like a ax plus b, right? Y equals to ax plus b. It's a linear function, right? So for y equals to ax plus b, and x has to be positive, what would be the smallest value for y when x equals to 0, right? But no, I'm sorry. If a is positive, then you try to make your x smaller. Then you will have the smallest y. But if your a, your coefficient is negative, then your x has to be larger. So it really depends on this term in the bracket. Okay? So let's observe. So these are just scalars. This is a scalar. Okay, they are just numbers. I put an S here because no. Do I put an S? Did I made a mistake? No. Vector. Yeah. It's going to be scalar. Because the first one is a vector, matrix vector. So vector, matrix vector basically is like a dot product between two vectors. So it ends up with a scalar. Yep. And so right here, they must be positive or 0, right? Because the way we define all the variables, they has to be positive or 0. So how can we reduce f? We now want this term to be negative. Want it to be negative. Because if x is positive, then its coefficient, I need it to be negative. Otherwise, I'm not reducing. I'm not minimizing a function. Okay? So, it's a very important concept for linear programming. From now on, we are going to do some selections. Right here, this is just to derive the equation, but we introduce a very weird way of handling the variables. We separate them. We separate them into two groups. Later on, we may not separate them just like this way. We can separate them in a different way. What do you mean by that? So let me quickly explain by here. In this particular case, just for you to quickly understand. If I have two equations right here, right? I can say, okay, this group is the basic group. then the other group, you guys are the non-basic group. So in this particular case, I'm treating y1 and x2 as the basic variable. The rest are just non-basic. And I'm going to follow the derivation right here. I'm gonna see whether I can find a good choice of basic variable and non-basic variable, so I can see this yellow box is negative. If I can do that, that would be a good choice of basic and non-basic. And I will tell you what's gonna happen for non-basic and basic. Okay, and let me explain more. How does it look like for choosing different sets of basic or non-basic? There are linear equations. I can just write S first and write X later, right? I can move their position. So my basic group can be Y1 and S2. So the other group will be non-basic. Okay, so later on there will be a procedure of choosing which group of variables are belonging to basic, the rest are non-basic. Okay, then now I will, after this explanation, I will now show you how to do it. So I'm going to directly jump into the solution process and then explain with directly one example. That's the easiest way to learn. So here's one example. Now let's minimize a problem. Okay, so this is a standard linearized problem. However, they are not equality constraints yet. They are all linear, but not yet becoming equalities. So what do? We will introduce slack variables. So I'm gonna copy here, paste it here. And I'm going to introduce, actually I need a larger space. So I'm gonna shrink that a little bit. So here is my x3, x4, and x5. So from x1 to x5, plus 0 x3 plus 0 x4 plus 0 x5. This is actually what's happening. And equals to 2, 7, and 3. They're all positive. After introducing the slack variables, all variables from x1 to x5, they are either positive or is equals to 0, and every inequality constraint has one unique slack variable, different from the other equation. And also in the objective function, the slack variables, the new variables, they exist, but they have 0 coefficient. So it doesn't actually change the objective function. Now, write everything into a vector and matrix form. So we are actually doing this. Okay, this is actually what's happening. Okay, now for the easiest way to start, when we are selecting, okay, well, tell me which part is basic, which part is non-basic. The easiest way especially for the course and also in the future, the easiest way is to pick up this part as basic and this part as non-basic, which means this part would be your CB transpose, this is your CN transpose. Okay, so let me stop being lazy. Let's just write down. This is basic. Okay, non-basic. So this would be your A, B. This would be your A, N. Okay? Actually, I will stop being lazy. I will write down all the X. So what does it mean for the X? These three are XB. These two are XN. I'm just grouping a different way, but I'm choosing X3, 4, 5. Now you are basic. So what does it matter when I do this? So from now on, for all the non-basic, we treat them as 0. So every time for non-basic, we just plug in 0. Okay. These are plug-in numbers, but when we plug in, we treat non-basic as 0. So basic variables, they are not 0. They can be solved. Here, A, B, X, B equals to small b. So XB equals to AB inverse small b. Can be solved. Okay? And it happens that now your AB is an identity matrix. The inverse is also identity matrix. So at the beginning, X3, 4, and 5 can be solved easily. They are basically 2, 7, and 3. Right? So basically your initial guess is 0, 0, 2, 7, 3. That's your initial guess. But that's not the solution, unless you're super lucky. Okay, but in this particular case, it's not the solution. I will tell you why it's not the solution. Now, let's take a look at this term. This term in the bracket. I want this to be negative. If over here you plug in whatever coefficient you have at this selection of basic and non-basic, and you plug in here, you noticed there are some term which is negative. And what's your current value of xn? Your current value of xn is 0, non-basic. So if you see the coefficient of 0 is something negative, that means you can try to enlarge xn. That's you. So the negative coefficient multiplying some value that was 0 now being enlarged to something else, your entire objective function will reduce. Right? That's the trick of linear programming. Originally, based on our setup, this is 0, right? And over here, if you find something negative, why don't we enlarge xn? Choose one. Change its value from 0 to something positive. Because here is negative. So negative value multiplying something positive is negative. So what does it do? It reduces f. Okay, so we are going to do that. Let me show you. So now, copy this term. When you do the exam, if I give you a problem of linear programming, I will give you this equation. So, what do you do? Okay. So you don't need to memorize it. Copy this term, paste it here. This is something we're going to evaluate, and let's evaluate. So what is my xn transpose? Now is -1, -2. What is my xb? 0, 0, 0. What is my ab? 1, 1, 1. Remember, this one needs a transpose. What is my an? Okay, it's a bunch of numbers right here. Compute this. And because of the 0, 0, 0, everything on the right hand side of the minus sign is 0. So at the end, you will have -1 and -2. So what does -1 and -2 mean? It means in your objective function, you have some scalar plus -1, -2 times your current non-basic variable. What's your non-basic? x1 and x2. In fact, your objective function right now looks like this. And now this is 0, this is 0. So there's a trick. I'm going to pick up one, either x1 or x2, make it positive. So which one are you going to choose? The one with coefficient -1 or the one with the coefficient -2? Obviously, we're going to choose the one with -2 because it reduces f more. Right? We're going to choose this coefficient. If I enlarge x1, it's a 1 times of the increment. If I choose x2, it's 2 times of the -2 times of the increment. So that's reduce f more. That's why we choose the largest one, the most negative one. So here we're going to choose the most negative coefficient. So what does it mean? This means x2 was non-basic. We want to convert it to basic. So what does it mean then? It means x2 later on can be any value other than 0. Okay? Once its status being changed from non-basic to basic, it could be a value that's positive, which is good. Okay? But when we do that, go back to see our standard form. We are always looking for it's always like this. We always have m basic variables, and we always have n minus m non-basic variables. Okay, so if I convert one non-basic to basic, then I need to know which basic will be converted to non-basic. So that will be the second half of the procedure. It's like a position swapping. So the linear programming procedure is like keep on swapping the roles of basic and non-basic until we find the best combination. So how many possible choices are there? So basically you totally n variables, right? It's gonna be combination of n variables and you are choosing m. Right? This is how in Taiwanese, in Taiwanese we do this Cn choose m, but this is only in Taiwan, right? This is what we learned when we were in maybe high school, right? We say Cn choose m. C means combination, but in anywhere around the world, no one writes in this way, but everyone writes. This is for Taiwanese. This is the standard mathematics symbol to write combination. Okay, so how many choices are there? Basically, this equals to n times. You need to write a lot, right? So this equals to n times n minus 1 until you will have 1 times 2 times n, right? And this should be n minus n. Is it? Am I right? Right. Yeah. So this is how many possible combinations you have. If you are trying to pick up the roles of basic and non-basic, there are this many combinations. So linear programming doesn't need to try all of these. If you can try all of these by computer, you can solve it. By computer, just okay, there are there are m selections out of n. Just ask the computer to do it, solve everything, and then there will be one which is the best. You can do that, but it's not smart enough, and it's wasting your. It's not efficient. So what linear programming is trying to do is to help you to find fewer possible combinations and then get the solution. Okay. Later on, we will use some graph to realize what happened. Okay. This is how many combinations are there. Combinations, solution combinations. Right? Then these many, but we don't want to explore all of them. So like over here, we have n equals to 5, m equals to 3. So what are the possible combinations? So pick up 3 out of 5. So 5 times 4, and n times 3, and 1, 2, 3. So at the end, blah, blah, blah. So there are actually 10 possible combinations. But later on, in this particular case, you will realize we don't need to try all 10 combinations. We only explore probably 3 or 4 times. We smartly choose 3 or 4 possible combinations, and then we found the solution. Okay. So this is a total combination, solution combination. Right? Okay. Now, we already know x2 is going to change its role from non-basic to basic. Now we're going to pick up one of the basic and then convert it to non-basic. And we're going to tell you what to do next. So we are using this equation here. We're going to recall this equation. Yes, this one. So recall, paste. So recall this one. And we are checking the dimension of every terms in this one. So we better use this to remind us. So just copy the whole thing. It will be easier for everyone. Copy the whole thing and then paste it down there. Paste and shrink. Maybe just maybe here. Okay, and then just as a reminder. Now xb is in the size of m by 1, right? AB is m by m, even after the inverse. B is m by 1. Okay. AN is m by n minus m. XN is n minus m by 1, right? This is correct. Now, what do we do? We will rewrite this equation into the following form. Okay, so xb plus AB transpose inverse AN xb xn equals to AB inverse and small b. Okay, and we are going to rename this guy as A hat, and we're going to call this guy B hat. Okay. Now we want to check the dimension of A hat and B hat. So this guy is n by m. This guy is m by n minus m. So at the end, this is m by n minus m. Okay, so B hat is having the dimension of AB inverse. So it's gonna be, sorry, I did it wrong. Sorry, I'm sorry. This box is wrong. Here, the whole thing is B hat. So AB inverse n by m. Small b n by 1. So B hat is going to be m by 1. Okay? Now, we are going to use our problem and visualize this this equation. So over here, we need our problem. Right? So let's get the problem. No, keep it here. Yep. Okay. Copy the whole thing and remind ourselves what is the problem. Okay, and we don't need this. Delete. Okay, good. So as a reminder, and we are just plug in. Okay, what is our XB at this point? It's X3, 4, and 5. Okay. What is our AB inverse? It's actually 1, 1, 1. What is our AN? Is actually some numbers here. What is our XN? It's gonna be X1 and X2. Okay, and oh, sorry, typo. This is plus right here. This is going to equal to 1, 1, 1. And B is B 2, 7, 3. Okay, right? And now let's just multiply the terms inside A hat and B hat. Let's just truly visualize how it's gonna look like for the A hat and B hat. So in fact, it's going to be like this. Sorry, this is 1. This is going to be X1 and X2. And this is, I did a typo again. This is plus. This is plus, right? So this guy is our A hat. This guy is our B hat, right? And we are going to visualize these as multiple linear equations. I will tell you why this is happening. So our basic variables, they are right now non-zero, and x1 and x2, they are right now still non-zero, right? Right now they are 0. Right now 0. Okay, but we already decide x2 will be increased to certain value. So only x2 to be enlarged. Even in the future, you have so many non-basic. Only one is being chosen from the previous step. That one is going to be enlarged. So, in fact, we don't need to care about the rest of the non-basic. They remain 0. So if there's something remaining 0, we can ignore that. Or we can just eliminate them in the current equation. Okay, so if we do that, we only care about this column, because the second column is the coefficient for the chosen x2. The first column of A hat means nothing in this iteration, because x1 is gonna be 0 all the time. Okay, so this one is the important column. Okay, so this is the important column in A hat for the chosen non-basic variable. Okay, that one is the important one. So when we pick up here, when we pick up the second coefficient, that is representing the second non-basic. So in the second procedure, the second step, when we have this equation, we are focusing on the second column of A hat. That's the one matters. Okay? So, in fact, you are treating this equation set as this. Oh. Keeping the columns and keeping the chosen one. You don't care about x1 anymore. That's what's happening. Okay, so what are they? There are 3 different lines, 3 different linear equations. So let's make a figure about these 3 lines. So here is x2. Okay? Originally, the value of x2 is 0. x2 was 0. Okay? So when x2 was 0, what's the value of x3? It's actually 2. So x3 was 2. And x5 was 3. So here, x4 was 7. But x2 was 0. Now I'm gonna enlarge x2. See how x4, 5, and 3 changes. But the way they change must satisfy this set of equations. Why do we need to satisfy this set of equation? Let's go back and see what is this equation coming from. We initially got it from this equation. What is this equation? This all the way back, we derive from here. What is this? Basically, the entire set of the constraint functions. So whatever we are trying to satisfy is basically whatever we had from the entire equality constraint set. We just transform its format in a certain way so we can better understand the numbers inside. So now, let's get back to here. So if we can enlarge x2, meanwhile, see how x3, 4, and 5 changes with satisfaction of the three equations up there, then we're okay, we're fine. We achieve what we want. We enlarge x2 and we still keep the equality constraints satisfied. Okay, now let's focus on x3 equals to 1 times x2 equals to 2. Right? So if I enlarge x2 by 1, then x3 equals to 1, right? So it actually is an equation like this. Just plugging 1, 1. Right? Another one, if I focus on x4 plus 2 times x2 equals to 7. So I got plugging x2 equals to 1. So I will have 5. So here, 5 is around here. So it's gonna be minus 2 here. Minus 2 here. Okay, so it's gonna be a linear function like this. Okay, now x5 times 0 times x2 plus. So x5 is gonna be 3 all the time. Even with increment of x2, x5 is 3 all the time. So these three linear equations actually looks like this. So which one do I choose to convert from basic to non-basic? Can anyone be smart enough to tell me? From x4, x5, and x3, when I increase x2, one of them was not 0, now it's going to change and become 0. Which one?
x5 equals to 3.
No, because x5 equals to 3 is still 3 all the time. It doesn't change to 0. Because even with increment of x2, x5 is 3. It cannot drop to 0. There's one variable is gonna drop to 0. Which one? You can already see it. Which one? Which one? x4? No, don't plus it. Just pick up one of them. x3 or x5 or x4. You're choosing x4. Okay. Now someone choose 4, someone choose 5. The solution is 3. That's fine. That makes you guys think. So let me explain why. I want you guys to learn from this mistake. Okay, now I'm going to increase the value, right? When I increase, sorry, that red line disappeared. When I increase x2, x3 drops, x5 remains the same, x4 drops as well. Okay, if I now increase x2 up to here, x3 already becomes 0, x5 remains the same, x4 drops as well, but I can no longer increase x2 because all the x has to be positive or 0. So here is the end of this procedure. I can only increase x2 from 0 to 2. x3 drops to 0. The rest do nothing. Just follow your equation up there. So at the end, right here, x2 becomes 0. x2 increase to 2. x3 drops to 0. And right here, x5 remains the same. and x4 drops to 3. So by doing so, x2 was non-basic, now becoming basic, and x3 was basic, now becoming non-basic. So it's a swapping of the role. x2 and x3 swap their roles. Well, why is it good for us? Because, let me remind you, whenever we pick up x2 to increase its value, objective function drops. Okay, but I want x2 to be enlarged, so f can drop. However, I don't know how much I can enlarge x2. So whenever I enlarge x2, I check on the constraints and see how other values is gonna change. You can enlarge as much as you want, however, all the values has to be positive or 0. That's why when you enlarge x2, your x3 drops, and it reaches to 0 the earliest. When someone drops to 0, okay, stop, you cannot do further. Otherwise, some of the variable will become negative, which is not satisfying the rules of LP. Okay? But if every time I need to draw this figure and observe, it takes a lot of time. So some testing procedure was introduced to help you to pick up x3 in a more effective way. So we call this procedure so-called the ratio test. So we are going to do the ratio test. Okay? So in the ratio test, what we are going to do is we're going to use BI over AIJ. What is I and J? So J is the column for the selected non-basic variable in the first step. Okay? So basically this one is AI2, because remember this is the whole thing is AIJ, right? And we are picking up J equals to 2. So here, this guy is AIJ. Okay, so we are going to do, and this is basically BI. The whole thing, this is BI. Okay, we are going to do BI over AIJ, basically AI2. So BI is gonna be 2, 7, and 3 divided by 1, 2, and 0. So this equals to 2, this equals to 3.5, this equals to infinity. Right? Over here, choose the smallest positive one. This is how the procedure works. And what does these three ratio tests represent? This is representing the selection of x3, this is x4, this is actually x5. So when we found smallest positive value, smallest positive ratio that is representing a particular basic variable, that one will be swapped to non-basic. So x3 was basic, now swap to non-basic. So why do we choose the smallest positive one? Because in this figure, when you have the smallest positive ratio, your value is going to drop and reaches to 0 the earliest when the non-basic value x2 increases. That's what the ratio test means in a graph. Okay. Actually, when I was a student, when my advisor taught this part, he didn't draw the figure, and he just said, "Oh, let's do the ratio test and choose the smallest positive value," and magically, iteratively, you get a solution. He didn't draw the figure, so it was. In the past few years, I realized if I draw this figure, people can understand more easily. Okay. Now, what's next? The position swapped. So we need to now go back to see the original problem. Okay, this is the original problem, right? And I'm gonna draw a line right here. Now, second iteration. Move on to second iteration. Whatever we did was the first iteration. Now we move on. But when we move on, what happened? We will erase these because the role changed. Okay, so the important part is come on. Okay, so let's focus on the original order. And I don't need this. The original order was basic, 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 non-basic, non-basic, right? Now, in the first iteration, we realize this guy changed to non-basic, this guy changed to basic. So in the second iteration, I am trying the other combination of the rows of basic and non-basic. And I'm gonna do the same and believe in this procedure. Every time this procedure is going to choose which non-basic should be enlarged, which basic should be shrink to 0. Keep on doing so, I should be able to reduce objective function gradually while keeping the equality constraint always satisfied. Now, when you do that, you can circle the same group together. So in fact, they are now the AB. And they are now the AN. So they may not stand next to each other anymore. Okay? But that's fine. This is how we're going to work on this problem in the second iteration. So let's take a look at, and also as a reminder, and check what we are going to do. So in the second iteration, I'm going to do it in the most efficient way. I'm not going to explain the in details. I'm gonna just tell you in your solution sheet what you write, what you will be writing down. Okay, you don't need to write a bunch. Okay, now, okay, second iteration. Let's do it. First, solve for this. So the first thing is you need to make sure you are not picking up the wrong guy. So this is going to be my Cn, and this is going to be my Cb. Okay, so to be careful, for the first time, this is your Xn, and the rest 3 will be your Xb. Right? In your exam, you don't need to, put a lot of arrows. If you can, just maybe draw some box. That would be easy. So now, Cn, I will have -1 and 0. Cb, I have -2, 0, and 0. AB, I have 1, 2, 0, 0, 1, 0, 0, 0, 1. Don't forget about the inverse. An is my -1, -2, -1, 1, 1, 0, 0. Okay, then solve it. So, if I give you same kind of problem with 3 constraints, you will have a 3x3 matrix inverse. So if the problem requires this and you don't have any tools to help you, you only have your hand, I will give you the equation for solving the matrix inverse. But the largest matrix I will give you in the exam is 3x3. So basically it's similar kind of problem, different numbers. Okay, please practice at home. Okay, I know solving for inverse, matrix inverse, there are different ways. Use the way you like. You don't really need to plug into the equation I gave you. Okay, and I already did it in the past, so I don't need to do it again. I did it, and the solution was -5 and 2. So these two numbers are the coefficients in front of non-basic in objective function. So what are my non-basic? Right now they are representing x1 and x3. And remember, we are going to pick up the most negative one. So, which means x1 will become basic in the next iteration. So, first step complete. Next, we are going to do ratio test directly. So the ratio test. So for the ratio test, you need to realize what is your capital A hat and B hat. So A hat, I had the equation earlier, is AB inverse AN, and this is AB inverse B. Okay, and actually it's right here. This guy. Copy, paste, copy again and paste. But some part is wrong. You delete. And here is my 2, 7, and 3. Okay, you need to compute those. So I already have it. It's gonna be -2, 3, and 1, 1, -2 and 0. This is 2, 3, 3. Okay, since I chose x1 as my most important column, most negative column. So for a hat, I'm going to choose this column. So this actually is my so-called Aij, where j equals to 1. Okay, now for ratio test, I need to do a hat over AI1 actually. Now is 1. So basically 2, 3, 3 divided by negative 2, 3, and 1. This is negative 1, this is 1, this is 3. And pick up this one. This is the smallest positive. Okay? And what do those represent? The 3 basic variables. So they are now x2, x4, and x5. Actually. So that means x4 you will become non-basic. Then what? Next iteration. That's it. That's for the entire iteration. You just do these, and then move on. You already know which to swap. So now I can copy the whole thing, probably up to here. Yeah, just copy the whole thing. Copy. Yeah. So next iteration, and then erase the old information. Okay. Eraser. Okay. Okay, I will erase these because it was in the second iteration it was like this. Now x4 you are non-basic, right? And x1 you are basic. So this is a new choice. And you can do the rest. Kill these. Oh. Kill these guys. Delete. Okay. So I'll do it again in a even faster way. I'm not circling anymore. So Cn is gonna be 0, 0. Cb is negative 1, negative 2, and 0. AB here, inverse it, An, 1, 1, nope. And it's gonna be, I have solutions, sorry, being lazy. So it's gonna be negative 1.33 and 1.67. So when you see a negative value, that means you can still decrease the function value even more. So not converge yet. So here, this guy is being chosen, the most negative. So this is representing x3. It's gonna be swapped. So this will become basic later on. Okay? So over here, copy this guy, paste it here, paste it here, and then we throw away this guy, and 273. So you still need to get those numbers. They are 667, 333, 667, 333, 667, 333. And this is 142. So over here, the first column is being chosen. Basically, j equals to 1, right? The first column. And we are doing ratio test 1, 4, 2 over the coefficients. Obviously, I don't even need to solve it. This is only positive one, right? And the last basic is x5. So positive. Or basically smallest positive. So it will become non-basic. That's it, and then next iteration. So I'm being even more lazier. I'm going to copy this part only. In your exam sheet, this is okay. Copy. As long as you know what you're doing. So, oops, come on. Next. And then paste. Right, next iteration. And so this one become non-basic. X3 become, oh, hold on. I did it wrong. Oh yeah. The first basic become non-basic. So this one, the first one. This one become basic. And last basic was this one. So this one become N. So in this iteration, it's gonna be B, 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 N, N, right? And do all these. Copy. And I'm sorry, I will be lazy this time. You solve it, you try it, and you will end up with 1 and 2. So in the objective function, the coefficient in front of the non-basic variable are positive. The non-basic variables are 0, multiplying with positive coefficients, so they are 0. You don't want to enlarge non-basic anymore because their coefficients are positive. If you do that, your objective function increases. So when you reach this step and the coefficient for the non-basic become positive, so all positive, converged. But what's the solution? Obviously, x4 and x5, they are non-basic. They are 0. Okay? How about x1, 2, 3? So from here, x1, 2, 3 equals to the coefficient on the right hand side. You can solve for x1 to x3, and they are the solution. That's it. Okay, and once we have it, let me see if I have it. I didn't have it. Let me solve it by MATLAB. This app conflicts with MATLAB. It will make MATLAB crash. Not crash, just slow. I just turned off some app. It makes my MATLAB slow. So I'm gonna just quickly use MATLAB to solve for come on. Turn off something. Sometimes it's like that. Come on. No, I mean, you just need some time. Say again? Oh, you want to see the notes? You want to see the notes? Okay. Okay. That's meanwhile we are waiting. That's for you to see. Yeah. Scroll down. Ratio test? You mean, oh, okay. Are you asking for this part? You mean, how come this is 3 by 2? Yeah?
We have subtracted one row matrix against 2 columns.
Yeah, so there are 2 columns. This column represent this choice. This column represent this choice. Because when we decide, okay, this is the one to be selected. So for the A hat, we will focus on the representing column. Why is it like that? Yeah, what was your question? CB transpose. Yeah. Oh, CB is these. So 3 by 2, 3 by 1. This is 3 by 3. This is 3 by 2. These are AN. This is AN, right? So at the end is Oh no, this is 1 by 3. So at the end, this is 1 by 2. 1 by 3, 3 by 2, multiplying 1 by 2.
The last one is 3 by 2.
Yeah. If you have n by p times p by q times q by r, at the end it's gonna be n by r.
I was expecting 1 by 3 matrix, so I think we can substitute.
No, it's gonna be 1 by 2. Yeah. When you manually do it, then you realize, okay, I need to get rid of these guys. Okay, so I hope my MATLAB is back. No, then I need to shut it down again. So, turn on that. Now, I don't need to use any of the codes from the past because linear programming code is very different. Let me start with a new code. I'm not sure if I can complete the coding from scratch in time, so let me see. Symbolic x1, x2, x3, x4, and x5. And c equals to and my a equals to small b is 273. Okay, so the roles. So let me have just call the role, okay? And or I will just call the basic, or just B. Initially 0, 0, 1, 1, 1. That means the last three are basic, the first two are non-basic. Okay, so every time I will be computing Cn, so how do I need to get B ID B equals to 0. This is called ID non-basic. ID basic, or just non-basic and basic. B equals 1. Does it work? This is optimization and 0324. Okay, solve. 1. B is let me see. No, it will. Sorry. I should do this. Like this. No, not like this. Okay. No, I can't do this. I can think of a better way. ID basic equals to 1 to 5 dot multiply b. If I do that, then I have 0, 0, 3, 4, 5. And then I will get rid of the zeros. So IDB equals to I don't need a 0. I need to get rid of the 0. So set different 1 to 5 and IDB and different size. IDB yes. Set difference is okay, so let me just do this. Okay, then I get a non-basic, and ID basic equals to set difference 1 to 5 ID non-basic. You probably have no idea what I'm doing, but I mean it works. I'll show you. See, non-basic is 1, 2. Basic is 3, 4, 5. So set difference is a comparison of set. If I use 1 to 5 vector, so 1, 2, 3, 4, 5, dot multiply 0, 0, 1, 1, I will have 0, 0, 3, 4, 5. The difference between 1 to 5 and 0, 0, 3, 4, 5 is the 0, 0 part. So the different part will be the output. So the difference will be 1 and 2. That's how I get 1 and 2. 1 and 2 from here for the non-basic. And then I do it again to compare 1 to 5 and 1 and 2. So what's different? The 3, 4, 5 is different. So that's how I get the basic. With this general code in the future, and when I change the order of the capital B, these two lines is always valid. Okay. It's not a meta course, but this is how I get it. Why do I need it? Because I need to do C ID of non-basic minus C ID of basic times AB. So A ID of basic and the whole thing. Inverse times AN. So ID of N and the whole thing. So this line basically computes for the coefficient check. So I'm gonna call this coefficient. And I need a small, the most negative. So the most negative, what do I do? So coefficient smaller than 0, or just multiply, or just use a for loop. That's easier. So for I equals to 1 to length of coefficient, if coefficient I is larger than, or I just say smaller than 0, that means it's negative, then I will keep, there's a called temp, or just a most negative value equals to 0 at this point. So the most negative one will becomes this. No, I need to do a comparison. If that one is smaller than the memory, then replace it. Right, so initially that value is 0. If I found another negative one, and if it's smaller than the most negative one, replace it. And I need to know, so basically the most negative ID is right now 0. So if I find it, the ID would be I. Okay? But I is just the order, but I need to know the real ID. So the ID for non-basic to basic equals to the ID, the ith one. Yeah, that's it. So if right now my non-basics is 1 and 2, if 2 is being chosen, then the second, so the index will be chosen. Yep, that's the first step. Second step, I need to do ratio test. So I need to compute for A hat and B hat, right? And I will basically do A ID basic inverse. I have here, basically this part. This is the A hat, and B hat basically multiplying small b. Okay, that's my A hat and B hat. But for the B hat, I only need the most important column. So the A hat J column will be the A hat, everything, and the important column. So most important ID here, the most negative ID here, that particular column. Now I do the I can use the for loop. I goes from 1 to the length of number of basic. So number of basic, basically IDB. Yep. And then I will do just call it RI equals to B hat ith divided by the A hat J ith. But sometimes I will be dividing by 0, so this is not good for computers. If this is, if the bottom part is 0, you do nothing. So I should have a memory of smallest positive ID now is 0. I don't need, do I need, yeah, I need a memory. So value, let me say 0, and then smallest positive ID. ID is 0. Okay? So if this is not 0, hold on. 1. Okay. If it's not 0, then we do something. If it's 0, we can skip it. If it's not 0, then I compute for the ratio. If Ri is positive, and if Ri is smaller than this guy, so I should make it infinity at the beginning, INF. So any positive value can be smaller than infinity. If it's smaller than that guy, I will keep a memory of it. So the smallest positive value will be that ratio. And the smallest positive ID would be this particular ID. That should do the trick. Oh, I forget about if we cannot find the most negative value. So right here, I need a flag. Initially, I need a flag. Here, I need a flag. It's a converged. It was 0. Convergency check. It was 0. So I do all these, and when do we convert it to 1? If the most negative value remains 0. So if this remains 0, that means we cannot find it's converged. So there's a convergence flag. So right here, when do we do all these? We do a while loop. While converged is 0, we will keep on doing this, right? That's the whole thing is inside a big while loop. And whenever this here becomes 1, then we can actually break it. So here, just break the while loop. Only when this is happening. So here, is it possible that we cannot find the smallest positive? No. This should not be happening. Only when the problem is yield condition. Otherwise, you should be able to find it. Okay, but now I need to know what is the ID from basic to non-basic. So it's gonna be the ID of basic of oh, here is not I. Here is most negative ID. Is it? Yeah, most negative. So here is most positive ID. So this is where then you figure out which. Here is the second part. Second part. Yeah, as a separator. So you know the first ID and the second ID, then you need to update. So when you move back to here, if starting from the, so you just need to update this capitalized B. So if this variable exists, exist variable. That means we are in the second iteration. So we need to update our capitalized B. So the capitalized B and ID non-basic to basic. You are non-basic means it was 0, so change it to 1. So B ID basic to non-basic, change to 0. So if I'm doing everything right, this is done. Let's do some pausing. I'm not sure. Okay, good. Now we are here. Step in. Okay. We have non-basic 1 and 2, basic 3, 4, 5. Good. Continue. Okay, some mistake already. Coefficient non-basic, coefficient basic, AID basic, sorry, should be reverse. Yeah. So every time we call A, it's actually everything column and the IDs. So I made a mistake here. A, so it should be like this. Should be okay now. Okay, run. Go. Coefficient. ID MB. Okay, go. Okay. Okay, coefficient. Like we did, -1 and -2. Correct. Done. And then most negative, I set it as 0. ID is 0. Okay, now check on every coefficient. Okay, now the first one was into the loop, so I update. The most negative value now is -1, and the corresponding ID is 1, but that's actually not the most negative one. In the second round, we found even more negative one, so the most negative value update to -2, ID update to 2, okay. Outside of the loop. Is the most negative value 0? No, so not yet converged. So what is the ID MB to B? The second one. So later on the capitalized B, the second one will be swapped. Now second half, compute A hat and B hat. Don't, okay. So A hat is, checking on our notes, A hat exactly the same, about B hat, exactly the same. Now, choosing the jth column, I am using the most, yes, this is okay. So the jth column, so the A hat J being, so second, like our notes, the second column being chosen. So 1, 2, 0. Okay, now set up smallest positive value as infinity and ID 0. Okay, now do the ratio test. Okay, if it's not 0, we do the division, and then okay, there's a ratio 2 here. Okay, is it positive? Yes. Is it smaller than infinity? Yes. Okay, now the smallest value is 2. The ID is the corresponding ID, which is 1. Is it? Now is the order, just order, not the exact ID. We will apply the exact ID in the final step right here. We can do the same thing again and go back. Second time, we realize the ratio give us 3.5. Now R is, see, the second one is 3.5. Okay, continue here. And then the next time the ratio is infinity, so it doesn't compute. And at the end, smallest positive is 2, and the ID is the first one. So the first one in the ID of basic is 3. So the ID from basic to non-basic will be 3. Okay, go to next round. Do we have ID non-basic to B as a variable? Yes. So the B was 00111. After swapping, the B becomes 01011. So it's gonna be non-basic NBNBB, right? Same as our notes, NBNBB, is it? Second round. Yeah, NBNBB. So directly move on to the third iteration and swap. After swapping, this is becoming BBNNB, is it? BBNNB, correct, okay. Next iteration, swapping is becoming BBBNN. Is it the same? Yes, BBBNN. Okay, now, because it's gonna converge, so let's see how it converges. Check on the coefficient. Coefficients are 1 and 2, just like the node. So there's no most negative value. So for this check right here at the end, the most negative value remains 0. What does it mean? It means converge, break, outside, finished. So, but at the end, what are the solution? So the solution would be this is a matrix, right? A matrix, and ID of oh, we need to do this again. Oh, no, just use the current one. IDB, the IDB inverse times B. That's your solution, but you need to know which are the three. So at the end, I will have. Oh, so I will say X star and IDB equals 2. But IDB is at the end, X is going to be a vertical vector. So I need this to be column 1, yeah, like this. So it's a vertical vector. And for the X star, the optimal, ID non-basic and 1 equals to 0. Everything becomes 0. So do it again. So, where? You cannot, column, yeah. Forget about this. So what is your X star? Oh, no, where? How come? Oh, do it again. Still mistake. IDB, and everything. IDB. I reverse it. Okay, now it should be okay. So X star 35300. So what does it mean? The optimal solution is 3 and 5. The other 300, they are slack variables. You don't even care about the value of slack variables at the end. It doesn't matter. What's important is x1 and x2. Okay, now let's try to 12:04. Do we have time to plot? Yeah. Let me do it super fast. So, figure. I need to do easy contour, and I need to just do a lazy version. Okay. Oh, I don't even need these. Lazy version. C1 and 2 times. No. Just C1 times x1. Lazy version. Not general code. C2. And then plotting in the zone of 0. Try this. Okay. And then hold on. Just to see. Come on. C2. Oh, x2. Okay, don't want to waste your lunch time. Contour. Okay, this is your objective function. Okay, good. And then we are going to say x is equal. Okay, and then I know the initial set because our non-basic. I should draw the constraint first. So easy plot, and then to draw the function, I need to say a11 times x1. Actually, on the right hand side, so minus plus b1. Everything divided by a12. Easy plot. So plotting in 0 and 10. Let me see if it's right or not. Yes, that's a first linear function. And then do set the color so it's obvious. H1. Do a for loop. Yeah, so I here. Okay. So I don't need an I here. Set. No, I can do it. Set each color black. Okay. Okay, only two lines? Only two. No. And then y limit 0 to 10. Should be 3 lines. Where are the third? Because is it the yield condition for plotting? Third line is it's a straight line. So straight line won't be drawn. It's a straight line. So just the third line is a straight line, so I need to just draw it separately. So let me plot 3 and 0. So 3 and 3, and then 0 and 10, and then in the black color. Yep. Okay, good. That's actually the original problem. Okay, and we are actually within this region, and the true solution is actually 3 and 5, but we initially was in 0 and 0. Let me plot it in the zone of 0 to 6, so you can see the whole thing even more clearly. 0 and 6. Okay. Oh, sorry. No. Do it again. Okay, we are actually. Oh no. Wait, here. 6. We are in this region. So when we set x1 and x2 as a non-basic, they are actually 0 and 0. So I can plot a 0 and 0 as our initial guess, 0 and 0. And let me do a circle red marker size 10. 10 should be okay. So let's do a dot. Okay. Okay. It's too small. Okay, so that's my initial point. Now every time at the end, I will quickly solve for my, x1 and x2, and then I plot out. So I will do this every time when we, at the end. So I'm gonna call it just x point. Okay, just call it x point, not yet the star, x point. And okay, so I will plot out x point 1 and x point 2, and copy the whole thing here so that you know where they are. It's quite important. They are following. Did you see that? It's following the wall, linear wall. And how come it doesn't plot out the last one? Because we didn't. Outside, we didn't ask him to plot. So that was the final step. So every time before you plot, I will pause so you can see. Pause right here. Okay. So this is initially we were here, and then continue. Next iteration, we end up here. So think about what we did. We will increase some variable from 0 to a positive value. And let's get back to our node. We realized the first time we increase x2. So that was the time we decide, okay, increase x2 needs to be increased from 0 to something. And then I asked someone, okay, where do we stop? Two guys gave me solutions, but wrong guess. That was the part, the ratio test was the part to allow you to move from 0 to 2. x2 goes from 0 to 2, and some other values become 0. Because this is just a 2D drawing, we cannot see x3 to x5. But when x2 goes from 0 to 2, some value goes to 0. And this is where we stop. And let's move on to the next iteration. We realize we bump into this intersection point. So that's where one of the select variable goes from 0 to positive, and it's stopped somewhere. So it's always following this idea, and it's always moving toward the linear boundary of this polygon, and it's trying to move toward the direction where the coefficient in the objective function drops the fastest. And the next iteration continue, and you bump into this final point and finish. You can no longer find any direction that drops objective function even more. Okay? Nice. I only occupy you 3 minutes. That's the end. I will send you the code. I didn't know I can finish in this fast, but I did. Nice. Okay, I will stop right here. If you have questions, come here. Okay, see you. Sorry about the rush.